Okay, so we left off, we talked about Gibbs free energy. We're going to talk about this thermodynamic and kinetic control, and then we're going to link back into Gibbs and finish him up today, hopefully. That's my cross my fingers plan to do. Come on. Oh, I need to turn this screen on too, don't I? So, thermodynamic and kinetic control. Here we go. So we're going to kind of talk through this. You'll have some of these problems to work on your own, and then we'll go from there, okay? So, when we talk about thermodynamic and kinetic control, come on, why is this acting up today? My computer is slow as molasses, y'all. Okay, so when we talk about Gibbs free energy, if we have a negative Gibbs free energy, that means that it's thermodynamically favorable. Remember, they prefer you to use thermodynamically favorable over spontaneous, okay? Not all reactions that are thermodynamically favorable actually occur. For example, for carbon diamond to carbon graphite, so the diamond in your ring, necklace, wherever, diamond center, wherever you want to go, that is thermodynamically favored to turn into graphite. Now, luckily, you know, if you have a diamond ring, that doesn't happen at room temperature because, you know, we wouldn't want that to happen. So why is that the case? Yeah, it's, you know, we've got the diamond here, the carbon, they have those strong covalent bonds, remember? And that's going to have this kind of covalent network solid that's going to be created. And to turn that into graphite, you're going to have to break down those bonds and remake it into a structure that looks similar to this, which is how your pencil lead works. So when you write on your paper, atoms and molecules of that graphite slough off onto your paper. That's how that works. And you're ripping apart some of these sheets of graphite, and that's what's being left behind on your paper and your pencil. But we need a very, very high activation energy in order to have that happen, which, you know, in real life, that doesn't occur at normal room temperatures. So that's kind of a good example of a thermodynamically favorable reaction that doesn't actually occur. And the kinetics are what is at play here. So this chapter 9 takes in almost every chapter that we've studied or every unit that we've studied up to this point and kind of brings it together. That's why 9 is such a bear to get through, because if you struggle with kinetics, if you struggle with redox, if you struggle with equilibrium, if you know, all of those things are now coming together in one place and kind of getting synthesized. So if you struggled in any one area, this unit is going to be difficult. Okay. So we say when these are prohibitive like this, that they are under kinetic control, which means that the kinetics of the reaction is going to determine whether it's whether it's going to happen or not. Okay. So if we have a huge activation energy that these things have to get over, a lot of times they're not going to input enough activation energy to make that happen. Okay. So some reactions that have a negative delta G don't occur is because of the high activation energy. Remember, we talked about those orientations. So in order for things to work, they have to be, you know, for the molecules to come together, they have to be oriented so that they bump together right. If I try to go like this with two molecules and get them to work, that, you know, it doesn't work. So the orientations have to be correct in order for that to happen. And then you have to have enough of those particles around so that they bump into each other. Like in the hallway right now, if you walked out there, you're not likely to run into anybody out there. But in another, you know, 20 or 40 minutes or so, you walk out there, it's a pretty good likelihood that you're going to walk into somebody. So you have to have enough particles in order for those to be able to kind of slam in together. Okay? So when we look at these charts, and you guys have seen these, this is your activation energy. So where your reactants started, the top of this, that is going to be your activation energy. And that's going to tell us with kinetics how fast that's going to occur. This section here, which is reactants down to products, when we have an exothermic reaction, that's where your thermodynamics is going to happen. Okay? So if we look at this exothermic reaction, for example, we're going to see that in here, this is going to be a positive for our delta S. And you can tell that because we're going from 2 moles of material down to, or over to 3 moles of material. So we're getting more disordered here. Okay. What is the sign for delta H? Well, they told us here that it was exothermic, so it has to be negative. When will delta G be negative? That's going to be always. Remember, we looked at those conditions last time in our last packet and saw that when we had a positive S and a negative delta H, that ends up being always. Okay. This reaction does not proceed at room temperature. Can you suggest why? Well, or can you suggest how that would happen? If you increase the temperature, then you might be able to get that activation energy going, or you could use a catalyst which lowers that activation energy. Okay. Now, if we look at the reverse of this, then we see that the delta S is negative. Notice that when we flip the equation, all of these things flip around. Okay? And you can't get that reaction to occur at room temperature. So you're going to have to do something to it. Okay? And then you have some more here that you can work with. I did post the answer key as well, so you have the ability to work through those. Okay? So now I'm going to switch over to that other packet. I can find it. This is the one that I gave you, right? This looks right for you guys. Where did this start in my notes here? Does this look like what you have? No. Did I post the wrong thing? Oh my gosh, I can't breathe. Oh. I get so hot with this mask on sometimes. Oh, I wonder if it's down here further at the starts. No, not the right one. I'll have to repost on. If I could ever get my act together. There we go. That looks right. Okay. All right. I skipped some of the first part on that document that I just pulled up because we'd already gone over it the other day in class. So just kind of as a summary of what we went through last week, we talked about, now she uses in these notes, she uses the word spontaneous, but you in your brain are going to switch that over to thermodynamically favorable. And I know you're all capable of doing that. So yeah.
So anywhere you read in here where she says spontaneous, in your brain, you're going to click over to thermodynamically favorable so that you get that correct on your work.
Okay. So we look at here, if we were looking at just entropy and we were looking at universe, positive is spontaneous, negative is non-spontaneous. So entropy declines whenever and you can see that. You can look at the moles of gas here, 3 to 1. So we've gone down with that. And then we talked about this free energy here, okay? And calculation of Gibbs free energy is ultimately decides whether the reaction is thermodynamically favorable or not, okay? Negative delta G's are thermodynamically favorable. Delta G can be calculated in several ways. We've talked about this guy, right? Where you take the sum of the products, the sum of the reactants. And this thing here, this prime here, means that these are at standard conditions, okay? So standard conditions are 298, 1 molar of material, and 298 for Kelvin, and 1 atmosphere for pressure. Okay, so when you see that, you know that that's happened. Now, this is what we looked at not all last week, but for several days last week, where we had the delta G equals delta H, T, delta S. We have to be careful with this section because remember that most of the time this is given in joules per mole Kelvin, and this is given in kilojoules per mole. Okay, so be careful with that. You've got to convert this guy over. If your temperature is not in Kelvin, you have to convert that over as well. Okay, so Hess's law works the same as Hess's in the enthalpy section. We just sum it up, and we can end up getting a new equation. Okay, so this equation you're not actually going to have to do on the AP exam. I think it's still important that you see it, you understand it, you know what's going on, but you are not going to have to do this on the AP exam. They pulled this one out of the curriculum. But I still, first of all, I'd like you to see it because I think it's worth your time. And second, I want you to see it because if you go on and take this in college, you will see this in college. Okay? So I like to give you guys a little bit of exposure. I do a lot more of that in a normal year than we have this year. I've had to pull a few things out that would supplement that, but that's just the way life this year has worked. All right, so what does this say? Well, this says that delta G that's not at standard conditions is going to equal delta G at standard conditions, which you could get by calculating up here. Okay, plus R, and we got to talk about that, okay, times T times the natural log of Q. And remember, Q was your products over the reactants raised to their stoichiometric coefficient. Remember how we did Q, concentrations? This was all back in equilibrium section. Okay, now, here is the kicker, and it's going to come up down here as well in this rat link section. Okay, here's the kicker. This is given to you in joules per mole Kelvin. This is going to be given to you in kilojoules per mole. So you're going to have to convert this, and this is where people oftentimes will get a problem down, this will show up on your AP exam down here, okay? And it applies to both of these. You've got to convert this. You have to divide the, are you not going to work for me, you son of a gun? You've got to, one more thing, eraser, pen. Why won't you work? All it's doing is acting like a mouse. I don't want it to act like a mouse. All right, well, you got to divide this by 1,000, and then that'll get you to where you need to be. Why can't things just work? This used to work in this. Tell me why it doesn't work anymore. I don't know. It's just so frustrating. All right, so you got to divide that out. This is called RATLink, and that's what I think of when I do this one. This one is on your AP sheet here. It's fourth from the bottom on this side, okay? And it is delta G prime, so that means that it's at standard conditions, which means that your T value is going to be 298 minus R, but again, we've got to divide that R by 1,000, and then that's going to be the natural log of K, so that's your equilibrium constant. Then we'll get into this one. I don't think we're going to spend much time with this one today. Maybe we get to a problem or two, but delta G prime, which means standard conditions, equals negative N. N is the number of moles of electrons. And when we did our redox reactions, these are the electrons that we canceled out. Remember, you had to multiply stuff until we had equal amounts of electrons on both sides, and then you canceled them out, okay? That's going to be the moles of electrons of a reaction, or a half reaction. You're going to look back at those half reactions. This is Faraday's constant. Again, that's given to you on your blue sheet along with this equation. And then that's going to give you your standard voltage, or 1 volt equals joules per coulomb. Okay, and we'll see if we get to any of those today. All right. So here we go. I need my snipping tool so I can snip this and put it over into Word so I can write. Because why would we want anything to work out? All right, so we're finding the free energy of formation. This better work. There we go. For the oxidation of water to produce hydrogen peroxide. So this is our equation here. We're given this information, and we're going to figure this out. So remember that our delta G of formation equals the sum of the, and that's my sigma. It's not the best sigma in the world. I don't know if I can do much better, but I'll try. That's a better sigma. Of the products minus the of the reactants. Okay, so they've given us these values. This is our product information here. Oops, products are over here. So again, be careful with these, because if you are given a huge list of tables, make sure that you're checking for the states of matter, because they will sometimes, like water, they'll have gas in there, and they'll have solid as well. So make sure that when you're checking those tables, if you're given a table of a bunch of figures, that you're picking the right one. Okay, so this is going to be minus 27.2, and we're going to multiply that by 2 because of this coefficient here. So that's where that 2 here came from. And then we're going to subtract. And here our delta G for this guy is going to be, well, we don't have any for our oxygen. It's just our water here. We're going to have a negative 56.7 times 2. And when you do the math, that ends up being 59 kcal per mole. Thermodynamically favorable, yes or no? And how do you know?
Because it's positive.
Correct. Good job. Excellent work there. All right. The next next one you should be able to do in your sleep. Let's see if you can do that one while I get it copied and pasted over. You have the answers down here. No. Let me know if you have trouble getting the delta H, delta S values. They give you the answers on there, so anything not make sense, let me know. Anybody struggling getting anything? Give you more time? Okay. There's the wrong one. Here we go. questions on this one? Anything that makes sense? Okay. And then if we go back over here. This one you're going to end up, it's diamond minus graphite. So this is, they already gave us the delta G's. So this is your diamond, is your reactants, and these are your products. So you're going to have negative 394 minus a negative 397. And so that ends up being 3 kilojoules for your answer. Does that make sense? Products minus reactants. All right. So then when we get into this guy, this again, you won't see one exactly like this on your exam, but I don't think that it's a bad idea to kind of go through it just to refresh yourself with like Q and, you know, our R values and all of those things. So we're going to go through it. But again, we're not going to see anything just like this, nothing this difficult on the AP exam, okay? I thought about taking it out, and then I'm just like, nah, you know, it may be good for us. Might not be a bad idea to run through that guy. All right, so at Q, remember if Q equals K, we're at equilibrium, okay? We've got 5 ATM and hydrogen is at 3 ATM, and they're converted to liquid methanol, okay? Remember that liquids are not part of K or Q. Pure liquids are not part of K or Q. So keep that in mind. So that means that this answer is going to be 1 over 3 squared times 5. That's our Q value. So 3 squared is 9. 9 times 5 is 45. So this is 1 over 45. Okay. So that is our Q value. If we do the little calculator with that, so that makes it a more manageable number with our calculator, it's 0.022. This was all, I did all this mental math, but then I used the calculator to get this value. Remember, Q values are unitless. We don't have units on Q's or K's. So we don't have to worry about those. So now we're going to figure out delta G. Here we want to calculate delta G. Yeah. So we've got to figure out delta G prime. So delta G, the first thing that we're going to do is figure out our delta G prime. And these they would have needed to give you a table for. Okay. So this one, delta G is a negative for this guy right here. Delta G is a negative 166. Our hydrogen is 0, and our carbon dioxide is a negative 137. Okay. So our delta G prime, again, these values would have had to come out of table. You don't have to memorize those. They would be provided for you. They just weren't provided for you in this problem. So I apologize for that. That's something I should have added in. All right, so we're going to take this negative 166 and we're going to subtract a negative 137. So our delta G prime is going to equal a negative 29, and that's kilojoules per mole. All right. So then we can take that, our delta G, we can plug that into this equation because I think we have everything that we need to plug in now. So this is going to be a negative 29 kilojoules per mole. We're going to add that to our R value. Remember our R value, though, before we start working with it, since this is in kilojoules, we need to get our R value into kilojoules. So that's going to be 0.0 So it was 8.314. So we've got to move it over 3 spots. So 1, 2, 3, and fill in the loops. So 0, 8, 3, 1, 4. That gets that into kilojoules so that we are per kilojoule, so we can get rid of that and take that care of that. We're going to multiply that by our temperature. It's set at 25 degrees Celsius. We have to convert Celsius into Kelvin. So that's 298. And we're going to multiply that by the natural log. Any more room here? Yeah, good. The natural log of this value right here. So you should be able to plug all of that into your calculator. Get your delta G, which is going to be a negative 38, and that ends up being kilojoules per mole reaction. Thermodynamically favorable? Yes? What if it's thermodynamically favorable yet it still doesn't run? What do we say that it's then? We just talked about it. Right? And we say that it's under kinetic control. Remember that? Talked about that at the beginning of class. So if that guy still doesn't run, that means that it's under kinetic control and the activation energy is too high. We need to reduce the activation energy with something like a catalyst, for example. Okay? Good? All right. So again, you're never going to run into a problem that's quite this bad, but you will run into a problem that is going to be close, and that's your rat link, and we're going to get into that next. Why won't that shove down? Why won't things just work for me, huh? Ah, technology. What puts food on my table, but it still can be frustrating. Did this? Oh, it stopped presenting. That would have been a mess for the people at home. Okay, let's try this again. Going back over here, go to the next problem, snip that guy. This is going to use our rat link. All right, here we go. So the first thing we need to do, our delta G is equilibrium. So we're solving for the equilibrium constant. We're solving for this guy right here. Okay, so that's what we got to solve for. We've got our overall reaction here using this data. We're going to try to figure that out. So delta G is something that we're going to have to calculate here. And we can calculate delta G, and this might be something that they would end up giving you, something similar to this, okay? They're going to give you your delta H's, they're going to give you your S's. You've got to calculate your delta G from that using delta G equals the delta H minus T delta S. So you got to do that first. And then once you have your delta G prime from that, then you can stick it in to all these other spots. So see if you can come up with your delta G here and calculate that. You should end up for delta G, it should end up being a negative 1,490.2. So that you should be able to do in your sleep right now. You should be able to easily work with those and be able to get those worked out. Able to get this delta G done? So then we're going to fill that in, and we're going to put that into our Ratlink equation. So remember, this is our Ratlink equation. If we wanted to solve for K, though, if we wanted to get K by itself, we would have the natural log of K equals, I'm going to divide everything by that, and negative I'm going to take over here on this side. It's going to be delta G divided by my rat, and then the link stays on this side. Okay? So I need to, and then remember, if we take e to the negative, or what is it? How do you do that? Yeah, e to the x. E to the x will get you out of that then, out of that natural log. All right, so we solve for delta G. Delta G was this guy. So we've got delta G is negative 1490.2 over, and we're going to divide that by the 298. And remember, we've got to move that decimal point for our gas constant. 8. Why did I get 231? I don't know where I got that from. That's not right. It's 314. Okay. So then when I get that, that's going to equal my natural log of K. So the natural log of K is going to equal, and I think that I got this right in here, negative 1490.2 divided by, make sure you do your parentheses down at the bottom if you do that in one full step. So that's, came out close enough. Negative 601.48 is good enough. So then if I take second natural log of that guy, I'm going to end up, oh, give me a 0. Well, it would be K is going to equal e to the negative 601, which is a really huge, stupid number, stupid high number. So our K value, K equals 10 to the 261st, which is a ridiculous number. Okay, so who knows what that is, but we'll just leave it at that. That's a lot of zeros to write out, right? Thank goodness for scientific notation. Okay, so questions on how to do those. Does that make sense, how those work? And then the next one's just another granddaddy problem, which you guys should be able to do. The delta G equals delta H T delta S. So you can work on that last one in there and then finish up 9.4 and 9.5 in your packet. Okay? So that gives you an idea of how to do stuff. These make sense? Dusting off some cobwebs from equilibrium. Bringing it all together. Okay. So there will be another video for you tomorrow, because I know how much you love listening to my